All right. Hello, everyone. I'm delighted to be here and thrilled that all of you are here. I also owe a debt of gratitude to all the other wonderful speakers before who really set the foundations very nicely and made my job a lot easier. I'm going to try and convey just a glimpse of some very simple ideas pertaining to how simple low-order models can be used in the context of specifically climate timescales, all right? And I'm going to do this through a few case studies. I'll try and remember to pause between the case studies, but you should feel free to interrupt me at absolutely any time. These are the kinds of diagrams you've seen a lot already before. The one on the left is interesting. It shows not only spatial and temporal timescales of processes that can potentially be included in Earth system models. I should say not all of these are included in Earth system models. The question the assessment was asking pertaining to this figure is, should they be included in Earth system models? How well would they be represented? How reliably would they be represented? And the reason I want you to have a look at this and glance at it later on is because I also want to set some context by saying that when we use simple idealized models to understand phenomena on climate timescales, be it also weather timescales, but in the context of today's discussion, climate timescales, we use simple models in a variety of ways, right from using them for things that are very poorly understood, whose climate reliability will be low, climate model reliability will be low, where we use idealized models in a more speculative vein, and we use them in the context of understanding, interpreting processes that we know we represent very well in Earth system models as well. The figure on the right shows essentially an artist's rendition of what a power spectrum would look like of weather and climate variability on a wide range of time scales, ranging from a few hours, a few minutes on the right to several 100,000 years on the left. As you can well imagine, there's no single time series which encompasses all these time scales. Some of these peaks might be familiar to you, some of them may be less familiar, may catch your attention later on. I want to draw your attention to the 100,000 year time scale, which we're going to discuss next. These are called glacial interglacial cycles. Scientists who study past climate, geologists have found over the last several decades that if you look at reconstructions of temperature, these are essentially what are called proxy reconstructions, indirect reconstructions of temperature. And this is carbon dioxide, which is measured from the concentration of CO2 in bubbles that are still preserved in ice cores. Essentially, they were in snow, the snow got compacted to ice, and this is obviously ice that has persisted throughout this period. And if you look at the association between the two, it's strong over a long stretch of time, but there's something especially special about the last 450,000 years. If you look at the power spectrum, there's roughly a 100,000 year peak. And so the community of paleoclimatology has done wonderful work trying to understand this phenomenon, not just pertaining to these 100,000 year cycles over this period, but also much longer stretches of time. But vis-a-vis this, they've sought to, of course, explain what they call the glacial interglacial cycles. And there are many interesting questions about the glacial interglacial cycles, their pacing, what's special about the last 450,000 years, the kinds of feedbacks, including cloud feedbacks that play a very important role. But I'm going to focus on the simplest question here. If one were to think about the extremes of these glacial interglacial cycles as steady states, one can ask what stabilizes them, right? So that's the question we're going to ask. And the coldest extreme, the coldest periods are called ice ages. As you can well imagine from this reconstruction, much of the northern hemisphere was ice covered. And we're going to think about a simple energy balance model that will allow us to interpret the stability of glacial and interglacial periods. So this is a simple energy balance problem where R out is the outgoing long wave radiation to space. You essentially draw boundaries around the Earth and the atmosphere, and you ask how much long wave radiation is going out to space. The Earth is not a perfect black body, but the outgoing long wave radiation, R out, scales increasingly with black body radiation. So you have an increasing relationship here. R in is the net incoming shortwave radiation. So what's coming in minus what's reflected back to space. Clouds obviously play an important role. But when you contrast glacial and interglacial periods, When you contrast glacial and interglacial periods, the biggest difference is the amount of ice cover, and makes a large difference to the planetary albedo. And so you can think about this system as having two states on the extremes. You have a fully ice-free state at low temperatures, a fully ice-covered, ice-free state at high temperatures, fully ice-covered state at low temperatures, where Rn is not sensitive to the temperature. In between, you have a strong temperature dependence. This gives rise to multiple intersections between the R out and the Rn curves, which are steady states. What are they steady states of? They're steady states of a one-dimensional model that you can write for global mean temperature. And the steady states are basically intersections of this graph with the t-axis. Okay. Mathematically, one can ask, well, what governs the stability of the steady states? And I leave that as an exercise for you to think about. Physically, I will point out that the outer steady states are stable. The inner steady state is unstable. And you can think about that in terms of what small fluctuations in the climate system will do, whether they will pull you back to the steady state or pull you away. And so I leave it as an exercise for you to think about what makes the outer steady state stable in this picture. In the picture on the left, physically, the outer steady states are stable because the outgoing long wave radiation, which is a stabilizing effect, is more sensitive to temperature than is the net incoming shortwave radiation in both the outer steady states. And the moment you appreciate that, you recognize that the utility of this model is not limited to the extreme idealization that we've made, where the warmer steady state is completely ice-free and the colder steady state is completely ice-covered. You can have some dependence, some variation with temperature of Rin, as long as the slope of that graph is smaller than the graph of the R out curve, you will still get two stable steady states, right? So the model doesn't apply merely to a completely ice-free and completely ice-covered state. It also applies to the realistic Earth, right? Where, for instance, now we're in interglacial, where we're not completely ice-free, right? And the glacial was not completely ice-covered. The ice didn't go all the way to the equator. So with that in mind, these are 1D systems that allow us to understand the notion of equilibrium. Well, people have asked, okay, well, what do we do next? How do we understand the transitions? And for these kinds of 1D systems, you can cast them as essentially a point moving down the gradient of a potential well. As here, you have two stable states separated by one unstable state. And you can ask, well, what kind of transition and what properties of the potential well and what underlying dynamics of the potential well will give rise to the kinds of results that we've seen in the geological record. And if you just had noise, for instance, seeking to induce a transition between these, you'll get this kind of power spectrum. And what's wrong with this? Well, you don't get the 100,000 watt peak, right? You also continue to get more energy at lower frequencies. All right? Okay. But I can stop and take questions, or I can continue. Yeah.
So when you say R out,
yeah,
you only meant the albedo of the planet, or both the long wave and the...
So you can think of one as long wave, yeah, yeah, and one is short wave,
okay.
Yeah, yeah.
Thanks.
Yeah. So R out is essentially net long wave balance. Rin is net short wave balance, right? And that's why you have two constant regimes where there's no dependence on temperature, the shortwave balance. Of course, there are cloud feedbacks, but there's an idealization where the story depends to first order only on what happens with surface albedo. Yeah. Yeah. Anything else? Questions? Yeah.
Unrelated, but what is the CP of this system?
See, the heat capacity of the system. Yeah, that's an interesting question. Yeah. So yeah. Yeah, that would include, on these timescales would definitely include more than the mixed layer of the ocean, right? Yeah. Yeah. Yes. Yeah.
So you have that C, D, Rin minus R.
Yeah.
But in short the curve, there's stable, there's unstable 6 point, then another stable. So the first thing that comes to my mind is that if C greater than 0, solution is increasing, that is becoming unstable.
Yeah.
When it is less than 0, solution is decaying, so it's got to stable fixed points. There are intermediate points that is present. So how do you model this equations? Like model here.
So you're talking about which points? You say there are additional points in between these two?
Yeah. Let's ask the first one.
Yeah. So can you give me an example?
So, for example, if you take C, D, T, D, R in minus R out,
Mm-hmm.
so what is the positive side? So that is the solution. On the other side, we have less than 0. Solution is decreasing. So one case will be stable fixed points. The other case will be unstable fixed points. Solution is going up. You might have a saddle in between also. Suppose if you modify the equation in such a manner, coming to that fixed point and just going to the other point. So how you model this nice curve that is having next.
So this is just an illustration, right? So you can map this balance to something that looks like this, where you have an unstable fixed point. It's just an example. So you could always construct more complicated diagrams to describe the kind of energy balance relationship that you expect, right? But this is just a simple illustration to illustrate the concept of stable and unstable equilibria. Yeah?
So is it there in NC 19?
So I'll get to Benzi et al. 1992. This is 1982. This is a very nice study on stochastic resonance, which starts with this idea and then asks, how do you get these transitions between the two states? Yeah? Anything else? Questions at this point? Okay. Questions? Yeah, go ahead.
Both diagram, I didn't understand what was the relative power of the y-axis.
Which diagram?
The one.
This one.
This next slide.
Yeah, this one. Essentially, it's a next slide.
Yeah, the relative power of the y-axis.
Yeah. Okay, so this is something we'll talk about in a bit. You start with the idea that you have two fixed points, right, that are stable, and an unstable fixed point in between. And then you ask, well, how do you get transitions between the two fixed points, right? And if the fixed points were stable and you have transitions between the fixed points due to the addition of noise, what is the power spectrum of the resulting time series? And so is your question why the relative power is increasing?
No, I just wanted to know what.
Yeah, so you do a power spectrum of the time series that you get when you have a potential well, right? You put a point in the potential well and you add noise and you generate a time series from it. Every so often, the noise amplitude is going to be large enough that you transition from one to the other and vice versa, right? Why is the relative power increasing? Is that the question that somebody has? Would anybody like to guess why the relative power is increasing in this case? Why does the relative power increase? What is the time series where the relative power is increasing? Is the power at smaller frequencies bounded? Non-stationary essentially gives you a non-stationary time series. Okay, so that's why the relative power is increasing. Okay, so here's our second case study. We think about a problem where in the context of monsoons, this is a context that's been very nicely set up by Vishal in his earlier talks. We're thinking about steady states of monsoon models. And we think about these as essentially the seasonal mean monsoon, the strength of the seasonal mean monsoon. And this was one of the early studies which started the investigation into whether monsoons are tipping points. Here's what's called a bifurcation diagram. Once you understand what the steady states are, so everyone with me on steady states, right? The idea of a steady state is clear. Okay, so once you understand what a steady state is, next question you ask is what happens to the steady state as you change the parameters of the model? All right, so you can well imagine that curve shifting down and the steady state's moving along the horizontal axis. And each steady state branch corresponds to a different feature of the system, right? So one of these corresponds to the stable steady state of the interglacial. The other is the stable steady state of the glacial, right? So each of them has a corresponding steady state branch. And those steady state branches for a different model, completely different model, are represented here, right? So essentially it's asking, how do the steady states vary as the parameters are changing, all right? So it's a simple model of ordinary differential equations. Yes?
So what kind, by parameters, what do you mean? I mean,
So there's some model with parameters, all right? So when you change the parameters of the model, you change the steady states of the model. Right.
for example, in this case, what would be a typical parameter? I mean, in this study, if you felt.
So in this case, the parameter is albedo. Yeah. So like was described earlier today, and we'll discuss that study in a moment, there have been studies that have shown the importance of nonlinear processes in monsoons for the energetics of monsoons and their nonlinear dynamics. Here's the early study which began this whole enterprise. Basically, what it shows is the steady state rainfall in a system of ordinary differential equations as the planetary albedo is changed. Okay, so the planetary albedo is a parameter. The system variable is the rainfall. Okay, the seasonal, you can think of it as a seasonal mean rainfall in a system of ordinary differential equations describing the mean monsoon. And what this basically shows is that as you increase the planetary albedo, this monsoonal branch becomes progressively weaker until at this point where the monsoonal branch completely disappears, right? So this is an example of what's called a tipping point. Further to the right of the tipping point, you only have a branch with very little or no rainfall. So this started the early investigations into monsoon tipping. The importance of it lies in the fact that at the same time, scientists were considering what they call tipping elements of the Earth system. Let's see what they mean. Term tipping point refers to a threshold at which a tiny perturbation can alter the state of the system. We introduce tipping elements to describe large-scale components of the Earth system, right? So these are large-scale components of the Earth system, and we critically evaluate policy-relevant tipping points under anthropogenic forcing, drawing on the recent literature. So the monsoons were included among tipping elements. I'm also, if time permits, I'll talk about the AMOC. The AMOC is also one of the tipping elements of the Earth system. And let's talk about the Indian monsoon in particular. The physics underlying this is something we'll discuss very briefly. The land to ocean pressure gradient, which drives the monsoon circulation, is reinforced by the moisture the monsoon itself carries. Any perturbation that tends to weaken the driving pressure gradient can destabilize the monsoon circulation. Right, so here's a schematic which Vishal described. There's a positive feedback. The idea is very simple. You have monsoonal winds bringing moisture. This moisture condenses over the core monsoon region. It amplifies the temperature gradients, which drive the monsoon in the first place, and that brings more moisture. So there's a positive feedback. As we'll see, you need a positive feedback for this kind of bifurcation to occur. There's also a nonlinearity in the model. So here's another quote from that paper. The abruptness of the transition emerges through an additional stabilizing effect of heat advection, which is cooling the atmospheric column. And so we'll see this, the implications of this balance in a moment. The point being that moisture is being transported by the monsoon winds. There's an amplifying feedback. And the question then is, does this make monsoons a tipping element? So I'm going to briefly describe one way of thinking about it in the context of something called the dry static energy balance. This is a quantity, a thermodynamic quantity, which combines temperature and height. This has its own conservation law. We won't get into the details, but the idea is you integrate this conservation law over the height of the atmospheric column, and you get essentially a simple model. You get a simple model which describes the evolution of the temperature difference between what goes on in the atmospheric column and what goes on outside. And the reason for that is the dry static energy in the column is closely tied to the temperature, the mean temperature of the column. So if you build a model for dry static energy under certain assumptions, you also build a model for the evolution of the temperature difference between what's inside the atmospheric column and what's outside. And I won't get into the details of the dry static energy balance, but basically there are various contributions to it. There's obviously radiative and conductive fluxes, but the ones that I've highlighted are the ones that are especially temperature dependent. So if we want to understand bifurcations, we want to understand processes that depend sensitively to temperature. And it turns out that these are the two processes that are temperature dependent. There's the latent heat, which is the kind of feedback that was described early on. You have stronger monsoon winds converging more moisture and therefore warming the column and therefore creating conditions for a stronger monsoonal circulation. You also have the export of energies, as were described in the talk this morning. And we're particularly interested in the export of dry static energy. And so since our column is essentially spanning the entire troposphere, we're primarily concerned with horizontal exports of dry static energy. But horizontal exports of dry static energy from the control volume depend on both horizontal gradients and vertical gradients, right? So they depend on horizontal gradients quadratically. So you can think of this as a quadratic advection term, where the winds themselves depend on temperature gradients. So temperature advection is quadratic in the winds themselves. So you have this second term. They also depend linearly on the winds, linearly on the state variable. And that's because of vertical stratification in this quantity. And vertical stratification is very important because there's a strong dry static energy gradient as you go up in the atmosphere, right? So this essentially means that so dry static energy is temperature and height. Height is going up, temperature is not coming down rapidly enough to make the dry static energy gradient zero. And this is essentially a statement about the vertical lapse rate of temperature. And so in the presence of this linear term, the dynamics is very different. But before that, let's think a little bit about bifurcation. Here's a simple equation for the evolution of a one-dimensional quantity of a scalar. And we already saw that the bifurcation points are essentially those that have been marked. The ones here, right? And these are essentially where the different branches meet. These are also the points where the function has zero slope because they correspond to minima and maxima. So to understand, and remember, these are bifurcations of equilibria. So the idea is, but the change in parameter essentially shifts the curve up or down or distorts it. But when you have a bifurcation, essentially it's at a steady state. It's at one of these points, and the slope is zero for these 1D systems. And therefore, we look at conditions under which this can happen. This can happen when the stabilizing and destabilizing contributions to the slope cancel each other, and that's what we're going to look at. This is the positive contribution, because as you converge more moisture, you warm the column, you bring in and you create a tendency to strengthen the circulation. This is the stabilizing effect, because when you have a warmer column, you also tend to export more dry static energy, both through horizontal gradients and because of the effect of vertical gradients, right? And so we're going to look at the balances between these terms. This term has a linear and a quadratic contribution. So we see that in the absence of stratification, we have this case below. We're essentially differentiating a quadratic equation with a linear contribution and a quadratic contribution, where the linear contribution has been set to zero. So it's a quadratic equation that's been differentiated, runs through the origin. I'm going to suggest that, analogous to the energy balance of the Earth, in order for the monsoon to be stable, the state dependent, the feedback that is stabilizing is more sensitive to the state variable than the feedback that is destabilizing for it to be a steady state. So the equilibrium lies somewhere here. And since the stabilizing effect vanishes at the origin, you must have a bifurcation point in this model. But the moment you're introducing a stabilizing effect, you push this curve up. You essentially push the red curve up, and you may get a bifurcation or you may not get a bifurcation. And so the point is, it's a strongly stabilizing effect. Dry static stability, essentially the vertical gradients and dry static energy are strongly stabilizing. You omit them, you're liable to get a bifurcation. You include them, you're less likely to get a bifurcation. So that's that. But the point is, this is a very simple model. The most simplistic models have omitted the effect, and therefore they come to one conclusion. As we see, the more complicated models have included the effect. Earth system model simulations that were done included the effect. They came to the conclusion that there is no bifurcation. The point of intermediate models is to bridge the gap between the simplest models and the more complicated models. They allow us to interpret what's going on in the more complicated models. So here's an intermediate model that comes essentially to the same conclusion. If you omit the effect of stratification, you get a bifurcation. If you include it, you don't. And essentially what happens is you're changing the season length, right? So if you reduce the amount of energy coming in, then you're reducing the season length until it essentially collapses onto a point, but there's no discontinuous transition in the monsoon. So here are the community Earth system model simulations, which essentially come to the same conclusion. There's the effect of albedo. There's no evidence of a discontinuous response to the albedo itself. And I think it's helpful to think, and here's an example where the most complicated models, the Earth system models, give us no reason to doubt that they're representing the processes relevant to understanding bifurcations. What the simplest models do is they help us interpret what goes on in the more complicated models, provided we include the relevant processes. And so here's what's going on. Essentially, you have bifurcation in the solution, but when you include stratification, the bifurcation happens for negative values of precipitation. So in other words, when you model these processes, you have a different system of equations for positive and zero precipitation, and there's essentially the systems of equations exchange relevance. And so the system of equation that you're interested in is really this up to here and this from here on. And the bifurcation happens at negative values of precipitation. If you exclude stratification, then you actually get more rainfall because the system is more unstable, but you then get a bifurcation at positive values of rainfall. And this is some additional, in the interest of time, I will skip this, but the idea is we're very interested in working towards a model hierarchy of this kind of system where you continue to include processes. And so I've treated a bit what we've discussed so far as simple models for what is really a land sea breeze, because we don't include the effects of planetary rotation. But if you include explicitly the effects of planetary rotation, you see what difference it makes. And we'd certainly like to work towards full Earth system models in this respect. And the idea is you get similar results. The results are qualitatively slightly different, but largely consistent. Okay, so in the time that I have now, I will talk a little bit about some work that you might have encountered, especially in the last couple of years. This is a paper by Hasselmann. Let's read the abstract. He says a stochastic model of climate variability is considered in which slow changes of climate are explained as the integral response to continuous random excitation by short period weather disturbances. The coupled ocean atmosphere land system is divided into rapidly varying weather system and a slowly responding climate system. So there's basically fast weather, slow climate. Weather is a stochastic input to climate. The climate does not feed back on the weather. The stochastic differential equation for climate is made, and this allows Hasselmann to study climate predictability in the context of chaotic weather, where weather is essentially noise on climate timescales. So if you think about weather as essentially weather events, you're essentially right, except one can also be more precise. You can think about weather in terms of weather versus climate in terms of the timescales involved. Here's a weather variable that has maximum power at high frequencies. Here's a climate variable which has increasing power at low frequencies. Another way to think about the difference between weather and climate is the dependence of weather prediction on the initial state to the phenomenon of chaos. Here's a paper that was published 60 years ago by Lorenz. I think the Lorenz paper had a couple of contributions. It made explicit the relationship between non-periodicity and instability for an English audience. This is a central result. That's why it's called deterministic non-periodic flow. The main result is essentially that a non-periodic flow is unstable. And so here's a statement. We don't have to worry about what a central trajectory is, but essentially it's unstable. A trajectory is unstable if it's non-periodic. What does that mean? Distances between initial conditions must grow. And in view of the impossibility of measuring initial conditions and distinguishing between this central trajectory. So the point is, most trajectories are central in these kinds of systems. Essentially, any point keeps returning to an arbitrary neighborhood of its point, an arbitrary number of times. And since central trajectories are unstable, all non-periodic trajectories are essentially unstable from the point of view of practical prediction. The other contribution of Lorenz was to introduce the first explicit model which gave rise to chaos, essentially discretizing the equations of Rayleigh-Benard convection. Here's a histogram of the time series of something that looks like X in a simpler model. Here's what the Lorenz attractor looks like. But the point is, on climate timescales, owing to the difficulty of predicting the state of a system that is chaotic, on climate timescales, essentially weather is seen as noise, but that does not mean it's random. It's a very systematic kind of noise. Here are some simulations of the path to getting something like the Lorenz attractor in a slightly simpler version of the model. And in order to get this, one can show that you essentially have to force the thermodynamic equations. You can't force the momentum equations. So the forcing in the Lorenz model comes from an external thermal gradient, and that's captured through this term Rx. And if I can replace Rx by constant forcing and get essentially the same result, but I can't put it in the momentum equation, right? So it's very systematic. And why is that? Because it's this forcing here that gives me the arrangement of equilibrium points that are very central to the genesis of the Lorenz attractor. And so it's very systematic, but the point is, on climate timescales is essentially noise. And that was the idea that Hasselmann used. But before we look at that, let's think about another example. You've encountered, coin tossing. You toss a coin. You don't know in practice if it's going to land heads or tails. There's a very nice paper that shows why that is. The idea is there are two parameters that are essentially relevant to the problem. There's U over G, the initial speed with which the coin goes up, divided by gravity. There's another parameter, omega. We assume omega is conserved, right? And these black curves essentially distinguish the regions between heads and tails. So if I know the initial state, I know whether it's going to land heads or tails, but we still think of coin tossing as essentially being probabilistic. And the reason for that is if U over G and omega are large, these regions get closer together, right? Anyone want to guess what the shape of these curves are? Sorry? No, the shape of the curves. Why? Product, right? Omega times U of G is 1/2 the number of, or 1/2 the change in angle, right? But the point is, here's an example where, and we can also compute the probabilities, right, as a relative ratio of the areas of the heads and tails. So they're alternating regimes with heads and tails. They're not equal, but then if initially we're ignorant about whether it's heads or tails, then heads and tails become equiprobable. So the deterministic process that essentially gives us what appears to be random. Another example, pinball machine, you strike a ball from a pin, individual trajectories may diverge, but we know the distribution. This thing is called the Galton board, after Francis Galton. The idea is you drop a marble and you get a truncated Gaussian distribution, right? So all of these are examples of things that follow deterministic laws, but that give rise to things, individual realizations that are not predictable, but across realizations, the distributions become very, very predictable. And essentially, Hasselmann used the same idea. So essentially, model of weather, model of climate. On climate timescales, remember he was interested in stochastic climate models. On climate timescales, weather is essentially unpredictable. So he says, well, it's a conditional, I'm going to treat the weather realization, this is the individual realization of weather X, as the conditional expectation of X given Y plus X star. X star is the anomaly. So this is essentially what you do when you do regression. You plug this into the equation for climate evolution. You Taylor expand. And the point is here, sorry, I played fast and loose with notation, but the point is the coefficients here are all functions of the climate state, not the weather state. And then you get a stochastic differential equation for climate. You can do various things with it. You can study its probability distribution. So these are things which were very well understood by Hasselmann's time, thanks not only to the early work on Brownian motion, but a lot of rich apparatus that was developed by Fokker, Planck, Kolmogorov, and others to study these kinds of equations, Brownian motion with drift, right? So this is a drift term, it's drifting towards, so there's some process which pulls the climate state towards some stationary state, and then you're trying to push it away. You can study the stationary probability distribution power spectrum. And then he also used tools of Fourier analysis developed by Norbert Wiener and others to understand the relationship between an input spectrum, which concentrates its energy in high frequencies, and an output spectrum, which concentrates its energy in low frequencies, right? So some of the same tools also can be used for this kind of analysis, although the work by Benzi et al. Was really an empirical analysis of the time series you get when you add noise to this and see, what are the realizations of time series that you get by adding noise to a system with two attractors like this. And obviously this is not good enough. So the next hypothesis was something called stochastic resonance. And I mention this because this is another example where weather affects the distribution of climate, but not the realization of climate, right? And I want to spend just a few minutes giving you a contrasting counterexample of that. The idea here is you have slow internal dynamics, and the barrier to transition between one of the other states is essentially given by the height. So you have slow internal dynamics here. The paper is not very explicit, but it seems to be motivated by the roughly 100,000 year cycle in the eccentricity of the Earth's orbit, which seems to play a very important role in the strength of the seasonal cycle. And one important finding in the paleoclimate literature is that interglacials are strongly coincident with the periods in which in the northern hemispheric summer you have large solar insolation. So, but this is a hypothesis. This is another area where simple models have been used in a more speculative vein. But the point is here you can get these regular transitions because you have strong enough fluctuations in the potential well interacting with large enough noise frequency. And here again, there's been a very rich literature in the stochastic dynamical systems literature on what is the nature of the relation between the noise distribution and the underlying deterministic fluctuations in the system with two potential wells that will give you this kind of dynamics. So very, very briefly, maybe I have 2-3 minutes. The premise of all of this work is when you think about, so there's really interesting work on weather, there's really interesting work on climate. Obviously, the timescales are very different. When you think about the interaction between weather and climate, a premise of this kind of analysis is, well, weather is essentially noise on climate timescales. But when you explicitly model the interaction of weather and climate using simple models, you can potentially get very different kinds of results. And that's the point of this. It's a simple modeling case study involving the AMOC, which is one of the tipping elements of the Earth system. You've learned about AMOCs from the wonderful lecturers over the last couple of days, and I'm really grateful for that foundation that they've set. So I'm not going to talk about AMOC very much, except to remind you, maybe you've encountered this paper by Stommel. Stommel was not only one of the early developers of a model of thermohaline circulation, but also in a follow-up paper in that same decade pointed out the importance of wind forcing. And subsequently, his co-workers and students have developed that idea much further. Not being an oceanographer myself, my understanding is not up to date, but here's an important paper I can point you to by Karl Wunsch. And Wunsch has done a lot of other work, but this is relevant because it points to the importance of wind stress on the large scale overturning, especially in the regions where this is important. And there's obviously some work done by the wind on the ocean circulation in the region where North Atlantic deepwater formation occurs. And there have been a lot of recent studies, and also just giving you one example based on some simple calculations of where atmosphere-ocean interactions seem to play an important role. So just here are some typical calculations. Broadly speaking, when you think about forcing to the AMOC, you can think on longer climate timescales, the forcing occurs through temperature and salinity. And when you think about some combination of temperature and salinity forcing the AMOC. Very broadly speaking, there are three different regimes. You can have a strong forcing on the right, which leads to an AMOC shutdown. You can have a small forcing where you still end up getting chaotic internal variability in the AMOC. And here, the AMOC acquires its chaotic internal variability from features of the atmosphere, although there are also more complicated ocean models which have chaos themselves. And you have intermediate forcings where you have this bistability phenomenon, right? So you have two steady states. It could end up in any one of those steady states. And so these are large initial condition ensembles where, both the ocean state and the atmosphere state have been initialized to different values, and you can get this bistability. And the point of the second figure is that you've essentially clustered each of these trajectories. So I can create I can change the number of clusters. And so I'm clustering these trajectories, and no matter how large my clusters number is, even if I create a large number of clusters of the trajectories, there's no way I'm going to be able to predict whether an individual cluster ends up in the strong overturning or a weak overturning state. And so this is for reasons we'll understand in a moment. Essentially what's happening is, and so this is a slightly different illustration where I'm only changing the atmospheric initial state. I'm not changing the ocean initial state. That's why you don't see the spread in the beginning, but then you see the spread at the end. And this bistability especially occurs when you have strong feedback from the atmosphere to the ocean. When the feedback parameter is large. When the feedback parameter is small, essentially the overturning circulation dies down. So in the presence of atmosphere-ocean feedback, you see the panel here. And what this panel is essentially showing is time, years, and this is a logarithmic scale, and the initial state of the atmosphere. So you...
Circulation.
Sorry?
What is that circulation?
It's non-dimensionalized. It's a low order model. Everything is non-dimensionalized, right? So units of time. Yeah. So you see these interlaced regimes with strong and weak overturning, right? On really long time scales. And this you only see when you increase the atmosphere. When you have strong atmosphere-ocean feedback, it does two things. It stabilizes the AMOC, right? But it also gives you these interlaced regimes of strong and weak overturning. And these are actually interlaced on all scales, what are called Riddle Basins. So our conventional view of basins of attraction and so on is based on much simpler concepts that we can visualize, right? So you have, we saw in the case of the global energy balance, you had two potential wells, two distinct basins of attraction. But here what's happening is the basins of attraction, which is a term I use loosely because these are non-stationary systems, so we don't have a good definition of basins of attraction. But nonetheless, that's why I call them basins, not basins of attraction. But these basins are essentially riddled, which means any part of one basin is punctured with holes, right? So folks in the dynamics community have developed a rich literature on this. And I'm going to, in my concluding comments, suggest that there's some new work to be done. But there are basically two kinds of ideas. There are these so-called riddle basins, where any part of one basin is riddled with a part of the other basin. Now, if you have two basins that are both riddled, then they end up being intermingled. And so any part of one basin contains a piece of the other basin. And so that's what's going on here. And what this shows is essentially in the colors, the overturning circulation after a certain number of years as a function of the initial state of the atmosphere and the ocean. And so initially it's a function of the ocean state. After 110 years, you don't know what's happening. It seems that what happens at 90 years kind of anticipates what's going on at 110 years. But the point is you can't anticipate what's going to happen at 90 years because of this phenomenon, right? So so the yellow boxes are essentially strong overturning. The blue boxes are weak overturning. And if I zoom into any of the yellow boxes, it will be comprised of yellow and blue boxes, and likewise with the blue boxes, right? And if I think about, I can draw samples and I ask, what's the probability distribution across different ensembles of the probability of getting strong overturning? Essentially, it's a binomial distribution. Okay. So this is a phenomenon that's been well studied in the dynamics literature, but not in the context of the kinds of non-stationary fast slope problems that we're thinking about, where there are weather and climate interactions. So there is scale separation, right? We get Riddle Basins, which means that fine scale initial condition uncertainty in the atmosphere has consequences for climate prediction in these models. So there's a lot to be done here. Here's just another illustration of what can happen. So for example, in this case, you have long-term predictability, but transient unpredictability when you perturb the vector fields. Here's just a quick illustration of what's going on. So every time there's a transition, essentially an unstable direction appears in the model, and that unstable direction is moreover strongly constituted by the atmospheric state, the state of the mid-latitude jets. So that's what the bottom panels are showing. But the point is, the wider literature and dynamics on this subject was developed in a certain context of systems that are largely stationary, systems that have symmetries in them. Those symmetries are broken when you couple atmosphere-ocean models, but you still get this phenomenon. And so the point of saying this is there is new work to be done. When we study dynamics and low-order models in the context of climate, we're not merely applying concepts that have been developed elsewhere. Simple calculations can also point the way to new concepts and ideas and ways of thinking about dynamics that need to be developed. Okay, so I'll stop here.